go ahead, stop the video, and let's flip the slide. So in the worst case scenario, what will happen is we will have like a chain of the nodes for our binary search tree, and then the time becomes a linear, right? To find, to insert an element, to delete an element, it's all gonna be theta of n, which we don't like. So ideally, we would like to do something to our BST, right? To prevent it from becoming unbalanced, or you could say too unbalanced. Ideally, of course, it should be similar to the heap, right? So it should be filled so that as many nodes as possible have left and right subtrees, right? It's kind of some kind of equivalent to the complete binary tree. However, it turned out to be quite impractical because then we will have to rearrange the elements, right? So after the node is added, we have to rearrange to move around some nodes, which we do not like that much. We will have to do some rearrangement, but it will be minimized. So, a workable compromise, right, if you would say that so. So we will insist that for a BST to be balanced, any node should have this property that the depth of its left and right subtrees should differ by at most one. Okay, not more. The solution was developed by the Adelson-Delsky, sorry, and Landis separately. So these two guys worked. No, I'm not sure here. Yeah, I think it's two different guys that worked on it, and then this one. So it was kind of the separate invention, but I'll have to check. I think it's two different people. Okay, and that's why the name for this type of tree stands for the abbreviation of the first letters of the last names, AVL. So AVL trees. Okay, so this restriction can be efficiently enforced each time a node is being inserted or deleted. So the worst case height in this case we are getting is, this is the exact value for it. So 1.44 natural logarithm of n. And you can find the proofs of this method complexity and the height of the tree. However, we have just kind of the statement here that it is this. Right. The book gives a little bit more comments about it, but that's basically it. So the performance of the insertion, deletion, find operation is back to the guaranteed theta of log n time, right? Which is quite good. We do like that logarithmic time. So here we repost our AVL tree property. So once again, the abbreviation of the last names letters, first letters of the last names. And here we state that for every node, the depths of its left and right subtrees can differ by at most one level. So we call these trees AVL trees. And what we do is we kind of grab the code for the binary search tree and we change it. For example, we will be reusing the tree node class, but we will add something to it, because you see they're mentioning the heights, right, or the depths. So each node will have one extra attribute, like the depth or the height. I think we called it height. Okay, and every time a node is being inserted or we go through the nodes, we will be doing some rotations there. The height will be, updated. So take a look at this example. These are two trees, but one of them is AVL tree and the other one is non-AVL. So once again, what's the AVL tree? It's a binary search tree that for every node has the following property. The heights or the depths of its left and right subtrees are different by at most one. So check out this 5. The depth or the height of its left subtree, remember how we counted? This is 0, right? So it will be 1 and 2. So it's 2. And for this subtree, its height is 1 and 2, right? 2. It's like the length of the path from the root to the deepest node, right? So the height of this subtree is 2, and the height of this subtree is 2. They are the same. Take a look at this the tree node, right? So the height of this left subtree is 1, right? Because it's like one what is it, one step in the path, right, from the root to the node, so 1, and the height of this one is 0. Same for the 8. The height of this subtree is 1, and the height of this subtree is 0. Because it is possible for our tree, right, to have a height of 0, we will start with the -1, if my memory doesn't fail me, for the height. So when the node is created and no value is assigned to it, and even if it is assigned, I think, by default, the height is -1, unless we update it, right? Now, check out this one. This tree is not balanced according to the AVL property because the height of this subtree, let's count it, it's 1, 2, 3. And the height of this subtree is only 1, right? So they are different by 2. And what it turns out is when the property is violated, this is what happens. The difference becomes exactly 2, okay? So we are catching the very first moment when, we have the issue, right? Okay, so what will we do with the insertion? Well, the normal BST insertion, you remember how we were choosing where to go, left, right, and then the new node is created, right? So the new node is made a leaf, right? And what we will do with the AVL property is we will insert an element and then we will rebalance. So check this out. We had this tree 5, 3, 8, 7, and 9, and everything was quite well until the 6 was inserted. What happened because of this is at 5, the height of its right subtree is 1, 2, so it's 2. And the height of its left subtree is 0, right? Because I don't have a path here, so it is 0. Now, take a look at what happened over here. Before 5 was inserted, everything was well, right? You could see that the height differences are at most 1. But when the 5 was inserted, you see these two levels, like 1 and 2, and then here we have only up to here. So at 12, at 12, the property is violated because the height of its left subtree, this is the left subtree, let's count it, it's 1, 2, and 3. And the height of its right subtree is only 1, right? So we kind of do one step down. Okay, and once again, as I noticed, it will happen exactly for when the depth is different by 2, right? Oh, no, and this is another one, right? So this also happens when the subtree has a depth of at least 2 already, right? This is another comment, okay? So it usually happens on these subtrees. Okay, so what will we do in this case? As I told you, the height or the depth of each subtree will be saved. It's a new attribute of the tree node object. Let me show it to you here. This is the new attribute, and this is Pythonian code. And once again, I forgot to remove this object, right? So we used to have 3 attributes: item, left tree node, right tree node. Now we also have the height. And as I promised you, if the node is nothing, right? If the node is kind of, it doesn't exist, then the height will be -1, right? We cannot use 0 because the tree node can have a height of 0, right? When it doesn't have any children, okay? So we cannot use the 0. Now, and when we create a tree node, right, by default, the height is 0. It's like we're assuming that this is a leaf, so it doesn't have children, and therefore its height is 0. Okay, now, let's going back, right? So we will perform the insertion, right, to the proper place. The leaf will be created. I think it is created, and then we rebalance, right? So for example, if we were doing the insertion into the left subtree, right, and this left subtree now is having the height of 2 more, right, than the right subtree, then we will rebalance the tree node at the node that we are right now at, where we notice the problem, right? Similar instance for the right subtree, right? And then when we will be updating the node's height, we will choose it to be the maximum of the height of the left subtree, the height of the right subtree, and +1, right? We'll add the 1 to the maximum. Okay, so we'll see some examples definitely, but First, what we do is we kind of see the Pythonian implementation of the tree node and this operation of get height, and we see the implementation of the same thing in C++. Although it's not quite implementation, it's a declaration. However, everything is similar, right? So for the constructor, we get the item, we get the references to the left subtree and right subtree, and they might be null in the beginning. And we also have the height, but you could see that we are not asking for it over here, right? So it's a little bit different from the Python. In Python, we get it here, right? And in C++, the constructor will just assign it. Height is equal to 0, okay? Okay, now this is the deconstructor, and unfortunately, the time when I was working on it, the tilde was moved to be like an asterisk or something of the T letter, but this is the deconstructor. Definitely we need the deconstructor because all these tree nodes will be allocated dynamically, right? So the space for them will be using the dynamic memory allocation, so we have to release them. Similar to what we did to the BST. This one is like, you know, capped, like we just copy and paste it. And once again, what we did is we grabbed the code of the BST tree and we modified it. Okay, and then 4 attributes, right? So the item, the left subtree, the right subtree, and then the height. Now, depending on where exactly the insertion was, we will be doing either 2 rotations or 1. So if we inserted into the left subtree or the left child, so this is what happened in this example. Let me show it over here. No, I don't have it. Okay, let me see this one. This one is, right? So at the 12, what we did is we went to the left child to the left child of the child, right? And then the insertion happened over here, right? So we went left, left, right? If we went left, left, if the insertion, and it doesn't matter where we went from now on, right? As long as we just go and left and, oh, actually, you know what? The property is failing here. It's 6, right? At 6, it's failing too, because the height of its left subtree is 1, right? And the height of its right subtree is -1. So this is where we will notice that the property has failed, okay? So this one then is not a good example, but we will see it. So just imagine that we are going left and left, right? From the node where the AVL property now is failing. So if we went left, left, we will have to do only single rotation and we'll have to kind of undo it. We'll have to rotate to the right. So this is the difference between the code that we have in our book and in the sources that you will be seeing online. So this rotation will be called the right rotation. But in our code, the way we will be implementing is it will be called left, left, because it's a left subtree of the left child, okay? Now, if we were following right, right, so we went right subtree of the right child, you know, and went somewhere there, it will be also single rotation. And we will have to also undo it. So we'll have to rotate back to the left. So this rotation, if you will be going to online resources, will be called left rotation. We don't use the names of the right rotation and left rotation here. We are using these words for them, like left, left, you will see, right, right, or single right, something like that. But then, if we were alternating the paths, so for example, we stepped into the right child and then turned left, or we stepped into the left child and then turned right, in this case, we will have to do the double rotation. And we will see all these examples, so don't worry about that. Now, if I remember correctly, the double rotation doesn't have a special meaning in the online resources, but we usually decompose it into the right and left rotation, you know, something like that. So those names you will see again, but it will be called double rotation. Okay, now in all of these rotations, what we do is we kind of undo the path that we followed. So take a look at this one. This example has the left. So what happened over here is before the 3 was inserted, everything was great, just perfect. Because the difference in these heights, you see, it's just one level. right? So everything is well. But as soon as 3 was added, you could see that this one is 2 levels longer, right, than this subtree. So exactly at the node 8, the AVL property fails. Not at 5. At 5, everything is good. The difference is 1, right? At 8. Now what happened over here is we went left and left. So left subtree of the left child. This is the single rotation. And what we do here is we kind of undo it. We rotate to the right, right? Now, how does the rotation happen? This 5 is kind of been replacing the 8. 7 becomes the child of the 8, and the 9 still is the child of the 8. So this is how the final tree looks like. And you know, when I was doing it in class, I could actually like show it with the fingers, right? Like how you're rotating it. So right now, just imagine that you're putting like the fingers on the tree and it's a little bit like tilted to the left, and then you rotate your hand to the right, right? Your fingers. So that's how it goes. Like it fives and it goes to the right, right? So 5 replaces the 8, 7 has to change its parent, now it's 8, and then we are done. Now, this is a similar situation with only one rotation, and you can see that we also are undoing the path, right? So what happened is that this 8 was inserted, and what we did, we went to the right child and the right child, right? So we kind of went right, right. So now we need to undo it. We need to do one left rotation. So imagine grabbing the 6 and just turning the tree to the left, right? So 6 will become the root, 3 will become its left child, and therefore 5 has to change the parent. It will be the child of the 3, and we are done, right? Okay, now let's continue. This is the example of the double rotation. And the double rotation is doing it by stages. So we are using the same type of rotations, the ones that were like for the single rotations, but we are doing one of them and then the other. So check this one out. What happened? We had this tree and the node with 6 was inserted. Now, how did it happen? We went right and then we turned left. So whenever we change the direction, and it doesn't matter what happens down there, what's important is that at the AVL, at the node where the AVL property falls, what has happened, right? So, and for the insertion of 6, what has happened is that we went to the right and then we went to the left, right? So what we will do is we will be unwinding the path. It's like we turned left here, so let's do the right turn. We went to the right here, let's do the left turn. And they are done one by one, and we start with the lowest one first. So here we go. First, we will do the right rotation over here. So the 7 will come into the place of 8. The 8 will become the child of the 7, and since the 7 didn't have any children over here, right? We won't have to change the parent, right? So it will be just changing the 7 to be the root, right? So we undid this step to the left, and then we will undo this step to the right, right? So we will be grabbing the 7 and we will be turning the tree to the left. So the 7 will replace the 5. This time 7 has a left child, so it will change the parent. 5 will become its parent, right? And then 7 will be the root of the tree. Now, as you can see here, everything is well arranged, right? For example, in this one, the difference is 1 level. In this one, this tree and this tree, they have the same depth. Everything is fine. Okay. Now, the way the methods are called, they will be called left subtree of the right child. Okay, because this is right child and this is its left subtree. So that's how the naming of the method happens in our book. Let me show you here. These are the names. Right subtree of the left child. Okay, and this is left single, so it's left, right? And you will see other names as well. Now here is the code which is really easy to look at. It is from Python, right? It's doing the insertion and it's using a helper method, which is recursive, right? Now, let's go over it, but then we will see the demonstration of it on the example. So it will help us to understand what's going on. So we start with inserting a value, and we immediately call the helper method and then pay attention to this info. This root, it might be updated, right? So the information about the root of the tree might be updated at the end. And it what happened over here, right? The 5 is no longer the root, the 7 is, right? So this assignment over here will help us to update the original root of the tree if that needs to happen. Okay, so first thing we check is if the T is what root are we using right now, right? Like what's our node that we are currently at is. If it is none, okay, it's time to create the tree node with the value that we are given, and this is our new tree node, right? Now, if it wasn't the new tree node, let me mark somebody, right? Let's mute. Yes, good. Yeah, everybody's muted. I was just checking. Okay. So now, if the tree was not none, right? So if if it was already something that we have there, it already exists. So let's see, where do we need to go, right? Do we need to go to the left or do we need to go to the right? So if our value is less than node's value, right? We will go to the left subtree. So we will say T left, right, is equal to, and then we call the helper method again. We are calling the same function of inserting an element into its left subtree, right? Now, after the insertion happened, after it's done, like of course we'll have probably several recursive calls there, but as soon as it's done, this is the time to check whether everything is good with the tree or this node is now unbalanced, right? So that's why we do it. We get the height of the left subtree, we get the height of the right subtree, and if the difference is 2, and this is exactly when it happens, right, then let's see where did we go to, right, from the child. So if value is less than the T's left item value, right, so it means that we went left, right, then it will be single rotation to us. To undo it, it will be called right rotation, right? And once again, what we check with the statement is, okay, we went to the left, right, but did we follow the left again or we went to the right? So this one makes sure that we went left, right? So the second move was to the left. Okay, but if we change the direction, if we went right, then it will be this method that is responsible for the rotation. Then what happened is we went to the right subtree of the left child. So it is a double rotation, right? Now, okay, if it happened that we are inserting the value into the right subtree, so in other words, our value is greater than the value of the node, then it means that we are stepping to the right subtree, right? Okay, so over here, what you would see is that the code is missing, right? We don't have the code for this case. This is the code that will be similar to the lines that we have over here. That was left as the exercise to the user, to the reader, and we do, keep it empty. So in the code that you will see, I do not put the code for it. So you have to think of what should happen over here, but the idea is the same. Right, so we are inserting a value into the right subtree. So then we will be talking about the T right there, right, over here in this else statement. So we will be calling the self-insertion help method on the T right, and then it's over. We have the same check over there, right? If the tree of the left subtree minus the height of the right subtree, it will be quite, it will be flipped. You have to switch them, right, is equal to 2 because we are inserting into the right subtree, right? So its height might change. So we should do the height of the right minus the height of the right of the left. So if it is 2, then we have to check, Did we go to the right? Did we continue going to the right, like in this case, right? So we went to the right, but did we step onto the right? If we did, then we'll have only one rotation and it will be called right single rotate, right? But if we step to the left, this will be the else case over here, right? Then we should say that the operation we need to call should be called left, right. So we went to the left subtree of the right child. Okay, so you will be reversing some of the things over here, but the idea will be absolutely the same. Now, after we did all of this, we need to update the height of this current node, right, that we are at this root. So we are saying that its height, its new height, is the maximum of the left subtree and the right subtree plus 1, because it's their root, right? It's like 1 up. That's why, right? Just imagine that, let me pull up the annotation tools. Okay, right? So we are at this node and we did some work. So we did something here, we did something here. So now when we update the height of this node, we get the maximum of these heights and then plus 1. And plus 1 is for this step, right? Either to the left or to the right. That's why. Okay, so that's why we have the plus 1. Okay, now let's see how some of these methods, not all of them, some of these methods work. Question? Okay, that's not for me. Okay, let's see how some of them, so not all of them, right, but only some of these methods work for this particular case. So what happened over here is we are inserting the 4, right? Because this is when it fails, after the insertion of 4. And the AVL property will fail over here. Not here, because their difference is 1, right? Not here, everything is good here, but exactly here. So from here on, let me see where did the insertion happen. I went left and then I did right. So it is the double rotation, right? And I have to undo this one, kind of rotate left, and to undo this one, rotate right. Right, but you see how the method is called. It's right subtree of the left child. So right subtree of the left child of this node. So it's all with respect to this node, right? This is the left child and this is the right subtree. Okay, and once again, what you might see online is you might see some other name. I'm just thinking of what can you see. Like I know what you could see for the single rotations, but for the double rotations, I didn't pay attention to that one. You might see some different name. Okay. Okay. Now what do we do then? First, as you can see over here, we will do right single rotation. Let me see. Right single rotation, T left. Like, you know, I'm talking about this, right? So this. And then we will do the left single rotation. Okay, I'm trying to see how will we end up doing this one first, because we need to do this one first, right? Okay, so let's see how the call is made. We will say T left, it's this one, it's this node, right? T left is equal to the self right single rotation. So kind of, you know, rotation to the right over. No, it will be rotation to the left, because here we call it the right. So it means that the insertion was right. So it will be rotated to the left. Let's see how it will be working. So we are right here at the moment. Now the grandparent will be set to the same node. This is the grandparent. And then the parent will be this one. This is the parent, T right? I'm just following the links over here. Now, what we are doing is we are writing down this information. Grandparent right, so it's this link, is now equal to the parent left. So this grandparent will be referencing to the 4 as the right child over here, right? Now, since the change happened for the grandparent, guess what? The T will see the change as well, right? Because these are just the references. So with this reassignment, we also change the information of the T, okay? So both of them, the 3 now, has the right child 4. Okay. Now, what happens to the parent left? Well, the parent left becomes the grandparent. Wow, right? So now its left child will be the 3. Here we go, right? We move it up so that it would look nicer because otherwise it looks weird. Okay, and then we say, hey, you know what? Do this adjustment. Now T is the parent. Okay. Now, what happened right here and right there is we did the rotation to the left, right? So it's called right single rotation because we stepped to the right? That we kind of undid it. So we did the rotation to the left, right? And once again, let's do from the very beginning. Like, look at 6. You remember what we were supposed, no, not this one. Wait, and go into the very beginning here. Okay, here how it was. You remember I was telling you that when we go to the left and then step to the right, we need to undo this rotation. We need to rotate to the left. So what do we do? 5 will be replacing the 3. The 4 will become its child, right? And that's exactly what this method does. We've just rewiring, right? Now this is the case. So 5 becomes the 3, right? And it has 3 as its child, and the 3 now has 4 as its right child. Right, so we did this rotation to the left, and it's called right single rotation. Okay, why right? Because we stepped to the right from the 3, right? You remember how it was? Here, we stepped from the 3 to the right. That's why the name comes. Okay, so we did this. Let's go this. Okay, now we need to adjust the heights of the grandparent parent, and we do that. We just don't show it over here. But then what's important here is we are going to return the information about the 5. So guess what? You remember that we had the assignment there. Let me scroll now back to the original. You see this assignment here, that the 6th left node will be updated. So that's exactly the return statement of this method. So this assignment will be done here. This T is returned, right? This T is returned, and it becomes the left child of the 6. Now, this was the second method to do. Once again, I'm going to slide back to these, I think, 2 lines of code that we had there. Just remember it, left single rotate. Here, you see we did the right single rotate, and now we are back to this one. So this is the next one we are working on the self left single rotate. Now this left means that we went to the left, right? And indeed we went to the left. So now we need to undo this move. Okay. Here. So our T is here, it's the 6. Let's say that it's our grandparent. And now let's say that this is the parent. So just watch it. The 5 is going to turn to the right. So 5 will become the root. 6 will become its right child. And since we don't have children here, nothing will be rewired in terms of the children. But watch it. Watch how it happens. So the parent is equal to T left. That's the parent. And now we say the grandparent left. So this is the link. This is the link we are talking about. Is now equal to the parent right. So this is the case if I had a string, like, a subtree over here, it would be attached as the left child of the 6, right? This is exactly the line. The grandparent left, so this link is changed to be the parent right. It's this one. But we don't have anything there, right? So therefore, we kind of have the disconnected tree now. Now, the next statement, the parent right, it's this one, right? It's this arrow we are talking about, is now equal to the grandparent. So this is how we rewired, right, the nodes so that the 5 became the root of the tree, right? So now we say that T is the parent. This is the one we are going to return back. That's how our root will be adjusted. And then, of course, we adjust the heights of grandparent and parent, right? Okay. So this is how these rotations are working, and we'll have an opportunity to play with them but I just wanted to talk about the code. So in the Python, and I'm just not even looking at it, we can go to our web page. Am I sharing? Yes, I'm sharing the screen with you. So over here, what you could see is you could see the code for the Python, and I actually have many more over here because I was printing them. Yes, like you see print levels. So you see all this code over here because we wanted to print it nicely. Okay, but then the get height is the function that we saw, and this one, you could just scratch it, right? Like erase it. Okay, and then what we have over here is the AVL tree, right? So it's all those operations, insertion help that we saw, and then only some of them. You see this exercise for the reader? So that's what we are told to do. And also like exercise for the reader. But one of these functions you'll actually find in the lecture slides. The code is given there, okay? Okay, now we definitely have some, I think, helper methods. No, it's just running it, just playing with the code. Okay, and what I would ask you is to play with it, change the code, fill those operations that are missing. But I'll show you the code that was written by one of our professor who is retired by now. His name is George Leibman. And what he did is he did convert the code into the CPP, and he did the pretty printing there, which is so nice. So let me go ahead and show it to you. Here it is. Okay, let me close the annotation tools. We don't need it. So this is the code of the AVL tree. And what I would say is definitely go over it. But this is the full code. So it doesn't have any things missing. And it also discusses the deletion. In our book, we do not discuss the deletion. So you will not be asked to show how the node is deleted from the AVL tree. And Professor Liebman just, did it for fun. Okay, so all the methods here are fully defined, and this is the code to kind of play with it. So it's called test AVL tree. Let me run it. It allows us to create the AVL tree from scratch. So check this one out. I'm creating the tree of 25, right? Oh, yeah, insertion 25. So this is my current tree. And then I'm going to insert the 10. So I'll say E, and I say the 10. Well, obviously should be to the left of the 25, right? Now let me insert the value of, let's say, 1. Now here what I'm looking at, the 1 should pop up over here. This is the 1, right? Now this will be unbalanced tree because here we have like kind of level 1 height and here it's -1, right? So it will be unbalanced, and therefore the code should rebalance it. Now, since we did the insertion left, it should turn it to the right, right? So the 10 should become the root, the 25 the right child, and the 1 the left child. So look at it, right? So, and what I would recommend is definitely play with this code and try to predict what should happen if you insert a value, okay? Now, let's insert more. Let me insert the 35, okay? So I'm going to insert the 35, and then I'm going to insert maybe the 7. It's still balanced, so it's like, our binary search tree, right? No, nothing special. Now let me insert the 8. You see what happened, right? It became unbalanced when I inserted the 8. And you could easily imagine it. It's like over here, the 8. Now the place where it will fail, let me just draw it, the 8. I'll draw it and I'll use the white color. Okay, so this is where it was supposed to be, the 8, right? The child. But what happens here is that the height of this tree is 1, right? Because this is the root, so 1 step down. And the height of this tree, which is not there, it's -1, right? So their difference is 2, and therefore it has to be rebalanced. Now, where did it fail? It's important of where is it failing. It's failing here, right? So from here on, the insertion is right. This is where we went. So therefore, it will be single rotation, and it will be to undo it, 1 rotation to the left. That's why the 7 became the root. 1 is left child and A is right child. Okay. So let's continue. Or let's think of something else. Let's do. I wonder if it understands the negative numbers. Let's do negative 10. Okay. So insert. Okay, I'm back here. Negative 10. Okay, and let me close my annotation tool again. Okay, so I'm here now. What I want to do, what I'm aiming at, is I want the property to fail again, but I want it to be the double rotation. So I'm thinking of this negative 10, and I'm thinking of going to the right. Unfortunately, it will not be that interesting, to tell you the truth. So let me skip this decision. Let me instead do this. Insert the 5, right? The 5 should go as the right child of the 1. Okay. So like the tree is really like spreading out right here. And then this is what I will do. I will insert another node, and it doesn't matter where. Should it be like the left child of 5 or the right child? It doesn't matter. What will happen afterwards is that the AVL property will fail at 7, because the height of this tree will be 0, right? And the height of this tree will be 1 and 2, right? So let's insert the 2. And you can see how the tree has changed, right? So no longer we have the 7 here, we have the 5. So let's try to see what has happened. I'm going to use the annotation tool again. Let me move it out of the way, because I think you see it, right? But it is really on the way. Okay, so I inserted the 2, and it was over here, right? It was the child of the 5. Now, the property is failing over here. So we always mark the node, the property, the AVL property fails, right? It is failing at the 7, exactly. Now, what happened at the 7? We went left, and then we turned right. And then the rest doesn't matter. What's important is we step to the left and we turn right. So we are going to undo all these steps. For example, this right, I need to undo it. I need to rotate to the left. So just imagine having 5 replacing the 1. And I will draw this tree over here because it's not shown over here. So the rotations are not shown. That's your responsibility to understand, right? But the result is shown, so which is really nice. Okay, so what happens over here is this 5 is being rotated to the left, right? So here is what happens. We get the 5 instead of 1. The negative 10 is its child to the left. Now the 1 is now the child of the 5. And this 2, guess what happens to this 2? It becomes the right child of 1. Oh, no, sorry. 5. I am undoing it. Yeah, no, so you know what I did? I did put the 1 into the wrong place. So look at this. I am rotating the 5. It gets over here, but this rotation, right? So let me do this. I'll erase this 5 because I need to put them a little bit lower. Otherwise, I won't have the space. So here is my 5. I'm rotating it. So here is my 1. And here is my 10, negative 10, and then the 2 becomes the right child of the 1. This is how the rotation happened, okay? So we did this rotation to the left, like this, right? Okay. Now we need to undo this step, right? Because once again, we went left and then right. So now we need to undo this step. So I have the 5. Let me finish up the tree. I have the 7. The 7 has the child of 8, and then it's the rest of the tree, which is not that important for us. But what we want to do is we want to undo this step. So we want to do this rotation to the right. Now what happens then? The 5 becomes the root. The 7 becomes its right child. right? And the 8 stays as the child of the 7. So this is what will happen. Let me grab the green one. So it becomes, sorry, I'm moving things up. Let me move them back. Okay, it's good, good. Nothing moved that much. Okay, so the 5 is getting 7 as a child, and 8 is is the child of the 7. So it going like this, and then 5 is connected to, what was it connected to? The 10. To this 10 that I have over here, right? Okay, so this is what you could see now, right? You could see the confirmation that we did all the turns correctly, all those rotations, right? And then the tree is still the 10, and I don't do the right branch, right? No, I did move it a little bit, right? Like this, here, yeah, here how it should be. Okay, so once again, we step to the left and then to the right. So we did the rotation, we undid the step, we kind of rotated to the left. That's how we got this piece, right? And then we undid this step, right? So we rotated to the right, but it's now 5. And when we rotate to the right, right, it means that the 7 becomes the child of the 5. Okay, so now we could continue playing with it. It's just, that's not that interesting. But definitely we have a nice demonstration from, I think, Virginia State University. I have that file posted, and what you can do is you can kind of double check what they have there and what you will be getting with this problem, with this program. Sorry, let me show you what I mean. So this is the handout that I am talking about. It's from Computer Science Department of Virginia, and they do this. They start with inserting the 3, and then they insert the 2, and then they insert the 3, the 1, and so forth, right? And they show what's going on there. They don't give the names to the rotations, which is good. That's why I have it. But they kind of show you what happens, and they always show you where the property fails. So for example, over here, the property fails at 3. In this example, the property fails at 3. In this example, the property fails of 2. So it is important for us to see where exactly the property is failing, because this is from the spot we will be looking from, right? And over here, they show that the property fails here, and so forth. So they have a very nice demonstration. They insert, I think, 16 nodes, like 16, and then 15 is the last one. And I think, yes, 14. That's it, right? So yeah, they insert 16 values there, because I remember that the 16 was kind of the greatest value, but they do not do it in the order of like 1, 2, 3, 4, 5. No, the order is slightly different. And then on the other side, what you could see is the kind of the summary of the rotations, like how it is done. I don't know if this one will be helpful for you, but I decided just to keep it in case if you find it out very helpful. Okay. But if not, just treat it the way we are doing it in our lecture slides. Okay. So let me now go back to the lecture slides here so that we could continue the discussion. So here I'm saying that we have the practice from the Virginia State University, but we also have our in-class practice that I wrote for ourselves. I tried to show the rotations there, so hoping that it will help us more. So I'm going to go grab this file. I already have it open, so just switch to it. And then if I remember correctly, for the extra practice, I suggested that you finish the Pythonian code and then something else. But notice this, we are not doing the deletion. And the search is like the search in the BST. It's the same idea. So we don't need to reinvent the wheel here. Let me grab the, sorry, I should stay in the same window, but let me switch to this tab, because this tab has the examples for us to practice on. Okay, here it is. In order to keep things simple, for the beginning, we actually point to the place where the property is failing right now and what happened recently, right? So this 3 was just inserted and it is violating the property at this place, right? Why? Because the height of this tree is, let's count, 1, 2, and the height of this tree is 0. So 2 minus 0 is obviously 2, right? That's when everything went wrong. So we are going to rebalance. How? Well, we see what's going on. Starting from this node where the AVL property fails, where did we go to insert the 3? We did left and left. The rest, we really don't care, as long as what happened to the child and the grandchild, right? So we went left, left. Okay, so then turn right, right? So this 7 will become the root. And just imagine turning it, right? Just, put your fingers or something like hands. Just imagine turning it. We grab this tree and we turn it to the right, right? So 7 becomes the root. 25 is its right child. And this child has a parent change, right? So it will be now the left child of 25. See how it happens. So this is our original tree, right? And this is our rotation. So as I promised, 7 became the root. 25 became its right child, right? The 10 changed the parent. It will be the left child of 25. And then 50 has, the same info. So that's the single rotation, right? And once again, what did we do? We undid our step. Okay, now take a look at this example. Everything is fine at this node, right? Because this one has a height of 0, this one -1. Check 25. Their heights are different by 1. Everything is good. So at 7, the AVL property fails. Why? Because this subtree has a height of 1, and then the subtree has a height of 1, 2, 3, right? So the difference is 2. Now see how the insertion happened. We went right and left, right? Like I tried to say right, but no, 15 is not here. So we went left. So right and left. This is the case for the double rotation because we changed the direction. You remember how we did that, right? So since we start with the child and grandchild, and then we do the parent and the child. Okay, so we do this one first and we undo it. So we rotate to the right. Over here, I copied the tree. So we have it over here, right? And this is what I'm saying, first rotation, child and grandchild. So this is the child, this is the grandchild. Just imagine turning the tree to the right. This 10 will be here. You see it here? This 25 will be its child, its right child, right? So this entire string to the right, is copied. But what happens to the poor 20? It has to change the parent, right? And it becomes the left child of 25. Okay, that's how we get this branch. Now, take a look at this. The AVL property is still not fixed, right? It's still like, at this one, what's the height of the left subtree? It's a 1, and here it's 1, 2, 3. So nothing has changed for 7 yet. But this is where the second rotation will finally fix it. The second rotation will rotate the parent and child. And since we went to the right here, it will undo it. It will do the left rotation. So here we go. This is what we start with, and this is what we get. We do the left rotation. So here the tree is turning left. 10 becomes the root. You could see it here. 7 becomes its left child. What happens to the poor 8? Well, it's rewired. It's now having 7 as the parent, and it's right child of the 7, right? Here we see the 8. The rest is all copied over, right, as it was. Now everything looks cute and nice, and the difference in levels we see is at most 1, right? And that's it. So the balance, the tree is fixed. It's kind of rebalanced, right? Something that I wanted to mention, and I cannot recall what is it. Okay. And you see that how that we spend so much time on these rotations because they are complicated. Deletion, if I remember it correctly, is more complicated. I don't remember how much, but it is more complicated, and we don't do it. The search is, as I said, similar to what we had for the binary search tree. Now, check this one out, right? The one was inserted, and the property fails here. I mean, it fails here, and it fails. No, it doesn't fail here, right? But it fails here. So the deeper we find it, that's the proper place, right? So it definitely fails at 5. Why? Because the 5's left tree, right, it has the height of 1, like 1 step. And the 5 right subtree, because there are no nodes there, it has the height of -1, right? So when we will be doing 1 minus -1, we'll get the 2. Now, what happened over here is we stepped left and left. So it's a single rotation. Now it's single rotation to the right. Can you think of what you should see at the end? Just take a moment and try to understand what should you see, right? Because what we are doing here is we are building the intuition on how to rebalance it. You will not be asked to code anything for, in terms of like, write the code for the L procedure to rebalance. No. What you need to do is you need to understand, and you do need to go over the code just to see how things are working, how this rebalancing happens with the code, right? It is important to be able to understand it, but you are not required to memorize the code, okay? So, is it something that you have imagined, right? Since we went left, left, we do only one rotation to the right. We undo it, right? So 3 becomes the parent, right? 5 becomes its right child, and the 1 is staying as the left child, okay? And I believe that's it, right? Yeah, that's all we practice slides that I have. So this is it. I will not be bothering you any longer. I know that we finished within 1 hour, but what I would ask you to do is right now, after the class, grab this PDF file from the Virginia State University and try to work on it. Because usually what we were doing, if during the in-class meeting, is I would distribute this to everybody, and, we will start working on this. Okay. So what I'm asking you is to go over this, and you know what, look at what they're inserting, try to do it on your own and compare it with the result that you are getting. Okay, so they have kind of, see this bunch of insertions, insert 3, 2, 1, and that's the result. Insert 4 and 5, it became unbalanced, that's the result, right? And over here, inserted 6 needs to rebalance, this is the rebalance tree, and so forth. So they always show you the result, what it should be. So it's a very nice and handy PDF file that I'm using for quite some years already. Okay, so that will be it then. Any comments? Nothing about the homework. We no longer have the homework, so only these suggested exercises. And then don't forget, you remember those short answer questions, right? Those true, false, multiple choice. Don't forget that you still need to go over them, right? So please use your time that we have, this extra time, for going over these questions for sure. Okay, because it's worth it. And just to reiterate what I have said about the homework number 19, in case if you missed our meeting on Wednesday. So I decided not to give you any programming exercise for the homework number 19. So only the Xi books, and this is the last quiz kind of, right? So make sure that you get all those points that we need, right? So that on the final exam, even if you don't get that good score, these quizzes will save you, right? Okay, so please continue working on your final projects. Don't forget. We have the office hours, not tomorrow, but on Friday, right from 3 to 4. So please swing by if you have any questions. Email me. Don't forget to submit the remaining homeworks on time, right? So like right now, the goal is to collect as many points as we can, so that even if we mess up on the final exam, and the thing is, it's not that it's hard, it's just that it has everything, right? So we really have to study and prepare and to remember everything. It's like, all this knowledge has to be active in our mind, right? So we have only one more meeting. We will discuss the algorithms that you already covered in CSI 35 in your discrete mathematics too. So for some of them, we'll look at the code and only for the breadth-first search. And the other ones we'll discuss and we'll see how to use it. It's a little bit different from CSI 35 because here we see how we store the information. So it's more in depth than what you had there, okay? Okay, so if you have any questions, please stay and ask. If you don't have any questions, you are free to leave. Let me stop the recording.